My name is Tao. I'm from Macau University of Science and Technology, and it is my great pleasure for being here to attend this amazing workshop. Today I will talk about the large-scale vortices in Jupiter. We have a lot of people in this room working on this topic, including the Keith Julian. He has have done some pioneer working on these large-scale vortices. This work was collaborated with Quinn Chan, Hans Meyer, and Kim Cho. So we know that the one major finding of Juno spacecraft to Jupiter is the discovery of the large-scale vortices in its poles. And as you can see that in the North Pole, there are several cyclones form a octagon. But in the South Pole, the cyclones form a pentagon. We call this as vortex crystals. So they're very stable and long-lived. The size is huge, ranging from 5 to 7,000 kilometers. And each cyclone, the spin period is about several days. And also for each cyclone, they oscillate around their local equilibrium points by a period on several months. Apart from the oscillations, is a whole pattern. This vortex crystal drifts around the pole retrogradely with a rate of 7.5 degrees per year in the north and 3 degrees per year for the south. So we know that the Jupiter's rotational period is 10 hours. So if we compare these periods with the planetary rotation period, then we can have the scale. The spinning period is on the order of 1 to 10, and the oscillation period is on the order of 100 to 1,000. And the drift period is on the order of 10 to 4 to 10 to 5. And we can see that these periods actually are very significantly different. So here are the questions. We have a bunch of questions here. One is on the origin of the vortex crystals. So it is unclear that how these vortices are formed and how deep are they, and what sustains these vortex crystals. And also, yeah.
Just a quick question on the previous slide, if I may. But you mentioned the drift rates; they're quite slow. How long is our observation?
It's about the observation is 10 years. I don't remember. Yeah, probably 10 years. But the Jupiter period is about 100 years or 50 years. Yeah, in decades. So another group of questions is on the dynamics of the vortex crystals. It is unclear how can they remain stable and what causes the drift and the oscillation of the motions of these crystals. So here I will try to address these questions. I will try to address the origin of the crystals by simulation and the dynamics of the crystals by analytical models. So yesterday, Rafa has given a very nice introduction on the large-scale vortices in the rotating convection. So here, since I'm interested in the planetary atmospheres, so for the Jupiter's atmosphere, the turbulent Prandtl number is about 0.1. So here I will focus on the simulation at this low Prandtl number at 0.1. And if you look at here, I have shown 4 simulations. From the right-hand side to the left-hand side, the rotational effect increase. And if you look when the rotation rate is not too strong, we can see the flow pattern actually is some kind of turbulence. And when we increase the rotational effect, here a large-scale cyclone appears. When we further increase the rotational effect, we can see apart from this large-scale cyclone, there is also a large-scale anticyclone appears. But we push the rotational effect to some crazy level to the limit near the onset of convection. then we cannot find the large-scale cyclones anymore. Only the multiple small-scale vortices appear here. So then if we want to generate some large-scale vortices by rotating convection, two conditions must be satisfied. The first condition is the flow needs to be highly turbulent. And the second condition is that the rotational effect should be strong enough. And here I have plotted the simulation cases in the phase diagram. The x-axis is the reduced rate number. We have introduced this before. And the y-axis is the Rossby number. So if you look at the figure, you can see that when the flow is turbulent, this part is the turbulent regime. So when the flow is turbulent and when the Rossby number is smaller, we can the large-scale cyclone and the large-scale anticyclone can appear. So yeah.
I have to ask. Input or output Rossby number?
This is input Rossby number.
Input Rossby.
Yeah. Oh. Mm-hmm. Good question. Okay, so obviously, for the appearance of large-scale vortices, we require a fast rotation and strong turbulence. However, I'm trying to apply this to the to Jupiter's atmosphere, but there's some difficulty if we use this Rossby number. There are two reasons. First, the Jupiter's atmosphere is highly density stratified, but this is really Bernoulli convection. It is incompressible flow, so we need to use a compressible flow to do the simulation. Another one is we have discussed before that this Rossby number actually is associated with the viscosity and conductivity, and also it is associated with the temperature difference between the top and the bottom of the atmosphere. And from the observational view, it is very difficult to measure this value correctly, accurately. So here I'm trying to switch to the compressible flow, and we have a model to solve this compressible system. This is the mass conservation and momentum conservation and the energy conservation. So similarly, if you look at the momentum equation, if you compare the advection term with the Coriolis term, then we can define the Rossby number. And the Rossby number actually can be defined as the ratio of the rotational timescale to the convective timescale. Here, the convective timescale, we can write it as 2h over u. So u is the convective velocity, and h is the depth of the atmosphere. So this convective timescale is actually the convective turnover time. So then the problem is how to define this convective velocity. So suppose we have a non-rotating Jupiter, and we can observe the flux. So if we look at the energy equation, this term is the convective flux, and this F is the input flux. So from the mixing length theory, we know that the flux should be proportional to rho u cube. So from here, we can know that the convective velocity is proportional to F over rho to power 1/3. So if we have the observational data of the flux, and if we know the density, then we can make an estimation on this convective velocity. Then since we have the convective velocity, if we know the depth of the atmosphere, then we can compute the convective Rossby number. Then now we change the boundary condition a little bit. We use a constant temperature boundary condition at the top, and we support a constant flux at the bottom.
Yeah, a quick question.
Yeah.
What was sigma in the last slide?
What is
Sigma?
where is sigma? Oh, sigma is the stress.
Oh, the stress.
Yeah, stress.
So can I just ask, is it a rapidly rotating system, but you're using essentially a free fall velocity?
This is not free fall velocity. This is when we have the
That's the
input
flux
flux.
version of the free fall velocity.
Similar to the free fall velocity. Actually, it is convective velocity.
Yeah.
I think he mentioned that let's assume that Jupiter is non-rotating and then proceed with that.
Yes. So we define this U as the convective velocity of a non-rotating Jupiter. So by this way, the Rossby number it will be monotonically decreased with the angular velocity. So that will be nice. If we don't do this way, then when the large scale cyclone appears, the convective velocity actually at a certain region it will increase. So that will cause some trouble because if the Rossby number can first decrease and then increase, then there will be some problem. Yeah. Right.
What about the beta effect?
Here we ignore the beta effect yet, but later we will introduce it. Okay. So here is our settings, and we have performed a series of simulations on the rotating compressible flow. Here, from the left-hand side to the right-hand side, we increase the rotational rate, and from the top to the bottom, we decrease the input flux. So we have here, all these variables are normalized. And the flux, so from the pattern, you can see that when the appearance of large-scale vortices actually is mainly depends on the Rossby number, and the flux only have very limited effect on the whether appearance of the large-scale vortices or not. So also we can find similar to the RBBC, we have two critical values. So when the Rossby number is smaller 0.11, a large-scale cyclone appears. Here, the plot is for the temperature. So for a low temperature, it is a cyclone. And when the Rossby number is smaller than another critical value, you can see here the large-scale anticyclone appears. This is pretty good because the criteria does not depend on the input flux. Yeah.
You mentioned that when you're compressible, you have this other length scale, the density or pressure scale height. Mm-hmm. So can you say something about how much density variation you have over the...
this is about 4 to 5 pressure scale height for the, So it is very deep.
What normalization did you use for the total flux?
I used the physical value at the top of the box. So we can have the observational data on that. Yeah. Yeah.
Apologies if you already said this. What kind of Mach number are you running at?
Our Mach number is 0.3, something like that. Yeah, it is smaller than 1. It is still subsonic, but it is almost reaches close to 1. But for this one, for this case, it is about 0.0 something. Yeah, because it has a lower flux. So now let's do some prediction. So we have mentioned before that we need the convective flux of a non-rotating Jupiter. That's how we make this prediction on the convective velocity of a non-rotating Jupiter. So we have performed a series of simulations with non-rotating compressible flow, and we got the flux, we got the density, so we can, and also we got the velocity, so we can plot the dots over here. And we found that the velocity agrees with the mixing length theory perfectly. So you can see the scaling is has an index of 1/3. And the Jupiter is here. So we can make an extrapolation to here so that we can make the prediction of the convective velocity of non-rotating Jupiter. Yeah, now we can get the convective velocity. It's about non-rotating Jupiter is about 4 meters per second. Yesterday, I don't remember who also made a similar prediction. It's about 0.4 meters per second. So this value is 10 times larger than their value. Okay, we know the rotation rate of Jupiter. And so because if the large-scale vortices in Jupiter is really generated by rotating convection, then the Rossby number should be smaller than the critical Rossby number. So since we have observed both large-scale anticyclone and cyclone in Jupiter, we will use the second critical Rossby number. Then we can make an inference on the depth of the atmosphere. So we can find that the atmosphere of Jupiter should be deeper than 500 kilometers. So we know that Juno has obtained the gravity data, and they can make an inference on this depth of atmosphere by gravity data. The prediction is the atmosphere is about 3,000 kilometers. So if that's true, then the Jupiter's Rossby number is 0.004. And for Saturn, the Rossby number is 0.008. So we can see this criteria is also valid for Saturn because we have seen a lot of large-scale vortices in Saturn. How about Sun? The Sun, today we have a nice talk on the Sun. We know that the Rossby number is from 0.02 to 0.2. So this is at the top, and this is at the bottom. So because the density variation of Sun is huge, the Rossby number is also varies with the depth. So if you compare with this critical value, probably in the bottom of the Sun, there will have some cyclone appears. But on the top, I don't know. We are not sure.
Can I ask you?
Yeah.
In your simulations, the vortices, they extend all the way across the
Yes.
planet, right?
Yes. And now, yeah.
For the polar cyclones,
Uh-huh.
you showed at the beginning we should take the critical Rossby 1, no? So it means that the depth is 5 times larger.
Yes, it can be. We have several simulations that it proves that the probably can extend several thousand kilometers. Yeah. And we just mentioned that the beta effect is very important since the motion of cyclone is highly depends on the beta effect. So here I will introduce a little bit on the beta effect. Suppose we have a cyclone in the northern hemisphere, and we have two eddies in the north end and the south end. And suppose these two eddies has zero vorticity. And we know here we have a higher F, the Coriolis parameter, and here we have a lower F. So when this eddy, it will move along with the wind of the cyclone to the left-hand side, and this eddy, it will move to the right-hand side. So when this one move to here, F decrease, so the vorticity will increase. It will create a small cyclonic motion here, and when this eddy move to here, then the vorticity will decrease, will be negative, and it will create a anticyclonic motion here. So the overall effect is that if you look at the flow here and here, these two eddies will tend to lift this cyclone to the poleward. If you look at the flow inside the cyclone, so the overall effect is the beta effect will move the cyclone poleward, and similarly, it will move the anticyclone equatorward. So this is, yeah.
But if you have zonal jets, you
Yes.
could have a zero PV. In that case, there's no.
Yeah, that's different because the jets can actually can survey the boundary for the motion of what is this. Okay, now we know that the beta effect is very important, so we are trying to include the beta effect in our simulation. We choose a small portion in the polar region here, and then we stretch it to be a flat plane. By this way, we can see that the angular velocity will point into the center line, and for each location, they have different omega. So we call this model is a polar gamma plane. Now we have performed 2 simulation cases. The case A has we assume the depth of the atmosphere is about 3,000 kilometers. For case B, we assume the atmosphere is about 1,600 kilometers. And you can see that both simulations, they can produce this vortex crystal structure. For this one, it is a pentagon, and this one is a hexagon. And it is, yeah.
I was just wondering, what do you do at the walls now? Because I guess before you didn't have walls on the box, but now
We
you
don't have wall here. We use a periodic boundary condition. But actually, if you look at this one, we use the periodic boundary condition, but the omega, it suddenly changes from this side to that side. Actually, when the cyclone passes along this place, it will kill the cyclone. Yeah. All right. Then how to generate these vortex crystals? We have several stages. So the first stage is that when we have a rotating convection, it will generate some very small vortices. And these small vortices, they will merge very quickly to grow up to the medium-sized cyclones. And after a while, this medium-sized cyclone can continue grow up by saturation. But this process is very, very slow. So we need to wait for a very long time for them to grow up to the large-scale cyclone. And then the beta effect will push all the cyclones to the pole and form this polygon structure. So that's the process.
are they merging in the intermediate stage, or are they growing?
Yeah, they're still growing.
They're merging still?
No,
they're just
the merging is
Just
almost
at the initial
ceased.
stage.
It is the merging process at here is almost ceased. Yeah. So here is the 3-dimensional structure, and you can see, yeah. Oh, it's almost the viscous dissipative time scale. So we needed to run the simulation for a very, very long time. Yeah. And if you look at the 3-dimensional structure, you can see that these vortices actually extend from the top all the way to the bottom. It is a very deep vortices.
Sorry, are they shielded?
Shielding, yeah, yes, there's some shielding inside these vortices. Okay, then how to maintain these large-scale vortices in the stable layer? Because for the Jupiter, we only have the observation in the stable layer, and we can we have seen this vortex crystal. There must be something to sustain this vortex crystal. So I have done such this equation is the equation of the change of horizontal vorticity. So this Chi here is the horizontal vorticity. And when we taking horizontal average and time average, we take a horizontal average on this horizontal vorticity, and we can express it as several terms. The first term is the tilting term, second is the stretching term, and this is the horizontal baroclinic term. This term is very small, so we can just ignore it. The tilting term is that suppose we have a horizontal vortex tube, and if we have a shear on the vertical velocity, so suppose the vertical velocity here is stronger and this is weaker, then this shear will lift this horizontal vortex tube vertically. So it will transfer the horizontal vorticity to a vertical vorticity. And the stretching effect, which means when we have a vertical vortex tube, when we shrink the vortex tube, the spin will faster. And if we stretch it, then we will spin slower. So that's the way we transfer the vorticity. So in our simulation, we have 2 layers. The top layer is a stable layer, and the bottom layer is a unstable layer. Yeah.
So delta is divergence, or?
there is horizontal divergence, and this is a horizontal curve, vorticity. Okay. So if you look at the data, here the blue line is the tilting term, and the red line is the stretching term. So in the unstable layer, we can see that the tilting term is dominant. But in the stable layer, the stretching term is dominant. The overall effect is the net contribution is the purple line. You can see that the purple line is negative in the unstable layer, but positive in the stable layer, which means we have a vorticity transfer from the unstable layer to the stable layer. Yeah, then that's how we maintain the large-scale vortices in the stable layer. Actually, the vorticity is pumped from the unstable layer, from the convection zone. And how about the energy transfer? We have shown the energy spectrum. This is from the observation, and this is our simulation. We can see that the pattern actually is quite similar. For the small scale, we have the chromograph decaying, and there's also a inverse cascade at this range. If you look at the observation data, we also have this range. So that's quite similar to the observation. So we have a short summary on the origin. For the it can be so on the formation. It can be generated. So the vortex crystals can be generated in rapidly rotating convection, and the depth can be deeper than 500 kilometers. And the vorticity is actually transferred from the convection zone to the radiation zone. Now let's go to the second part on the dynamics. So the first question is how to remain stable for these vortex crystals. We have two kinds of models to explain the stability. One kind of model is the empirical model, trying to do in the numerical simulations and try to find some hints on this stability. One example is the work done by Li Chen. Use a two-dimensional shallow water simulation and find that the anticyclonic shear is very important to remain the stability. So our three-dimensional simulation found that actually the Coriolis effect should be stronger enough to maintain the inertial stability. But for this kind of model, it is not very clear. To understand the underlying physics, we will better use the analytical model. One example is proposed by the Gabriel and Caspi, and proposed that the force balance between the push force from the polar cyclone and the pull force from the beta effect should be balanced so that they can remain stable. Here I will explain this analytical model a little bit. So as we have mentioned before, the beta effect is very important. For a cyclone, if we have a cyclone, the beta effect tends to pull the cyclone forward. Now, suppose we have another polar cyclone, and he just seated at the pole. When two cyclones are very close, the polar cyclone tends to push this cyclone away. So we have a push force and a pull force. How about if these two forces can be balanced, then we can find the location the equilibrium is achieved. So Gabriel and Caspi, they have made a calculation on Jupiter's atmosphere. And if you look at this red curve, you can see that the x-axis is the latitude and the y-axis is the net force. And when the balanced, there are two equilibrium points, but only one is stable. Why is that? Suppose this is the equilibrium point. Suppose we have a small offset from the equilibrium point. When the net force at this one is pointed back to the equilibrium point, then it is stable. But if the net force is pointed away from this equilibrium point, then it is unstable. So although we have 2 equilibrium points here, only this one is stable. So yeah, this model looks so far so good, but the problem is, yeah.
Just to better understand, do they have to assume some kind of shape of the vortices to do this?
They have computed so because we have a beta effect, they can compute the force from the beta effect, and they also compute the force from this polar cyclone to this cyclone. So this force is from this polar cyclone, and this force is from the beta effect. When these two are balanced, then it is equilibrium. So they find there are 2 equilibrium points here, but only this one is stable.
When you do the calculation, don't you need to assume some vortex structure to
Yes.
the force?
Yes, the vortex structure, Li Chen has given a nice formula on that, so from the observation. Now, is the equilibrium point really unique? So we have performed a series of simulations. Here we have 3 simulations. All the parameters are almost the same, except for the separation distance. So for the first case, the separation distance is 7. So separation distance means the distance between this one. And this one, the separation distance is 8, and this is 9. So from the simulation, you can see that all these patterns can remain stable, which means the stability, the equilibrium point is non-unique. So if you look at it carefully, for this pattern, the whole pattern drifts progressively, and this pattern is almost steady, and this pattern drifts retrogradely. So then why is that? Why is the simulation result is different from the theoretical prediction? So let's go back to the basic Newton's law. So suppose we have such kind of vortex crystal. Yeah.
Are these still inelastic simulations?
This is this is a simulation, but now we'll go to the analytical
But it's still inelastic, your simulations.
This is a 2-dimensional barotropic simulation. Yeah. So if you look at this cyclone, then all the rest of the cyclone will have a push force to this cyclone along this direction, and also we have a beta effector pull the beta effector along this direction. So when these 2 forces are balanced, we call it is a static equilibrium. However, in Jupiter, we know that this pattern drifts around the pole with certain angular velocity. And imagine that we have a satellite orbit the Earth, then we, apart from the gravitational force, we will have a centrifugal force, right? So when these 2 forces are balanced, a dynamic equilibrium can be achieved. So this is similar in the vortex crystal. The balance should among the pull force from the beta effect, the push force from the other cyclones, and a centrifugal force from the drift. Now we are trying to include this. So we suppose we can write down the force equation. The A is the acceleration. So we can write down the equation on the acceleration. This acceleration will depend on the locations of all these cyclones, and also depend on the omega d, the drift rate. So how to achieve the equilibrium? When the acceleration is 0, we can achieve the equilibrium. So since we have a total number of n vortices, we can have n equations. However, we have n plus 1 unknowns. So when we solve the system actually is underdetermined. The possibility is that it might have infinite solution for this equilibrium. So the omega d is indeed non-unique. And then now let's take a look at the force balance. We call the drift force is omega effector, and this force is the cyclone interactive effector, and this is the beta effector. So the beta effector is proportional to the gamma. The gamma is the second order derivative of the Coriolis parameter. So it is a constant for a planet. And so the omega effector is proportional to the drift rate. When this interactive effector is overcome the beta effect, then this will be positive, so that the pattern will drift, the omega d is positive, so the pattern will drift prograde. And if the interactive effect is smaller than the beta effect, then omega d is negative, and the pattern will drift retrograde. So that explains why in our simulation we can have the program motion and the retrograde motion. So how about omega d equal to 0? If omega d equal to 0, that is static equilibrium. So from the static equilibrium, we can obtain a critical gamma. So when the real gamma is smaller than the critical gamma, which means the gamma effector is weak, and the pattern will drift prograde. But when the real gamma is larger than the critical gamma, then the gamma effector is, when this effector is smaller than, when the real gamma is larger than the critical gamma, the gamma effector is very strong. So the pattern will drift retrograde. Okay, so now we can compute all these terms. And if you look at this figure, this is the critical gamma, and the x-axis is the separation distance, and this y-axis is the critical gamma. And for different curve, represents the m-fold vortex crystal. When m is equal to 3, which means it is a triangle. When m equal to 10, it is a decagon. So for different L, we can get a gamma. Then we can compare. If we have the gamma of the Jupiter, then we have the separation distance of the vortex crystal. Then we can compare the real gamma with the critical gamma to check if the pattern is retrograde or prograde. And now we have a theory on the drift. Then how about the stability and the oscillation? It is very simple since we already have the equation of the acceleration. Then we can linearize this equation. So suppose the displacement of one vortex is proportional to e to the power of sigma t, then we can get an oscillation equation. So here, the left-hand side turns to be sigma square x, and the right-hand side can be, if we take the Jacobi matrix as capital A, then it is ax. Then the sigma square, yeah.
Sir, please finish yours.
Okay, the sigma square is actually the eigenvalue of this Jacobi matrix A. And then if the real part of the sigma is negative, then the pattern, the whole pattern will remain stable. When real part of sigma is positive, then it is unstable, right? And how about the oscillation? The oscillation period is just the imaginary part of the sigma.
One question. So I may have missed something, but my feeling is that you're basically calculating the velocity induced by other vortices, and also the beta effect at the center of a given vortex, right? Yeah. So that basically will give you the drift velocity of that vortex, which then directly give you the xi dt, not d square x.
We take a further derivative to time, and we get the acceleration. Yeah. So we have an induced velocity, and we take a further derivative.
So then on the right-hand side, you would have something that is dx I dt.
So we already have, we can write down the equation of dx dt of equal to v, right?
Yeah.
So we take a further derivative to time, we get the dv dt. That's acceleration.
Okay, but on the right-hand side, your original velocity is written as a function of xi, right? And then when you take time derivative, you will get the xi dt on the right-hand side.
Yeah.
Yes.
Yeah, yes, we can get the analytical solution actually, but that is very
I
complicated.
guess we can talk about it.
So I didn't show it here. It is a little bit complicated.
Oh, okay.
Yeah. So here, now we check whether the vortex crystal pattern can be stable or not. So here we have choose different gamma for the planetary for the planet. This is gamma equal to 0, gamma equal to, all these values are normalized, 10 to minus 4 and 10 to minus 2. So if you look at the pattern, here the x-axis is again the separation distance, and the y-axis is the maximum value of the real part of sigma. So when this value is positive, it is unstable, but when it is 0, it can reach a neutral stable. So to remain the pattern to be stable, our requirement is that the separation distance should be large enough. So if the vortex crystal has a large separation distance, then it can remain stable. Okay, so and from here, when the m increase, the number of vortices increase, we need a larger L to remain stable, which means if we have a pentagon, suppose the separation distance is this large, we can remain stable. But however, when you have an octagon, the separation distance should be larger to remain stable. And here I have shown the simulation to verify our theory. Actually, you can see that all kinds of vortices from m from 3 to 10, they can all remain stable. And if you look at this case carefully, these two cases, case F and case G, for both cases, m equal to 8. But for this one, it looks like a Sudoku, which is very similar to our observation in the North Pole of Jupiter. So now we can, yeah.
Do you always have a central cyclone?
Sorry?
You always have a central cyclone?
Yeah, yes.
You could also work without it.
I have tried, but in that case, it is unstable because the beta effect will pushes the cyclones inward into the pole.
Well, in the lab, I have with a stable structure with no central one.
Yeah, that is for when the gamma is 0, it can remain stable. So when we have no beta effector, when there's no central cyclone, for this case, they can remain stable. But when we have the beta effect, they will always have a beta force that will push this cyclone inward because you have a very large space in the center.
The neighbors, they could also push outward. Don't take that into account in your model, right?
For anticyclone, it can push outward, but for cyclone, it only pushes inward. The beta effect.
We'll discuss it. And your central vortex is not moving around; it's fixed in the center.
Yeah, yeah. It can walk around.
It can.
Yeah. So now we are trying to okay, I will finish it quickly. Okay, so we are trying to investigate whether a Sudoku can be stable or not. And here we have make a similar stability analysis. Here the x-axis is the short axis distance, and if you look at this axis is the ratio of the long axis distance to the short axis distance. This curve is for the data in the right-hand side for the ratio. And when this ratio is equal to 1, then it is a perfect octagon because these two axes are equal. But when they're equal to square root 2, then it's a Sudoku. So we can see that when the separation distance is shorter, actually it forms a Sudoku. But when the separation distance is larger, they form a perfect octagon. So why have we observed the Sudoku in the Jupiter's North Pole? It is because the separation distance is not that large enough. And we also observed that in the South pole, the pentagon is offset from the pole a little bit. So why is that? We also made some stability analysis. We can see that suppose we have for one of the vortex we has a different strength, then the whole pattern will shift offset from the pole a little bit. So the reason is that the vortex crystal can be shifted from the pole when the vortices have varying strength. And I tried to calibrate the data for the vortex crystal in the North Pole and the South Pole. Here is the periods. For this one is the spinning period. It is on the magnitude of days. And this is the drift period. It is in the magnitude of years. And it is, for this one is the oscillation period. And it has a magnitudes of month. And we can see that we have, actually we have a bunch of the oscillation period because our eigenvalue problem has multiple eigenvalues. Yeah, so here is the short summary. The equilibrium is non-unique, and it can remain stable when the separation distance is large. And the drift and the oscillation, the drift can be retrograde or prograde depending on the relative strength of interactive effect to the beta effect. And the oscillation, they can oscillate at multiple frequencies. Okay, that's all. Thank you.